It's a great pleasure and a unique honor to introduce today's speaker here in our I²CNER seminar series. This afternoon we are honored to have Professor Jack Brouwer, all the way from the University of California at Irvine. As you know, the University of California at Irvine has a lot of activity in energy, like us, and it is the home of the National Fuel Cell Research Center. It is a leading institution in the United States that explores all kinds of concepts for power generation, transportation technologies, and in general tries to introduce what is the best mix of energies, renewable energies, fossil fuel energies, to optimize optimum solution energy pathways for the American society, and of course for the international, world. Right? So this is why I²CNERs and the National Fuel Cell Research Center's interests, as you see, are having a great deal of overlap. So we are privileged today to have Dr. Brouwer to present us the Fuel Cell Center's, his own activities, and see how our international community get bridged. In other words, this is another effort that we are doing here in I²CNER to bridge the two sides of the Pacific, science and technology. So Dr. Brouwer finished, got a PhD from MIT, and he is a world expert in energy systems, in the thermodynamics of the energy systems, and the analysis of those systems. So he has a lot of experience in general concept of energy. And as you know, energy is a concept that involves many fields of science and technology. So today, Dr. Brouwer will present somewhat a holistic approach to those issues, and his talk is Design, Control, and Integration of Next Generation Power and Energy Systems. Dr. Brouwer, the floor is yours.
Thank you for that kind introduction, Professor Safranis, and thank you very much for coming to my talk here today. I very much like the way that Professor Safranis pronounces my name, because I am here to save the world. Jack Brouwer, to save the world, right? But there is an R that is right after the B, so I am distinguished from him in really saving the world by introducing sustainable power and energy technologies. And like you guys here, I hope to make those advancements that are required so we can actually use these technologies. This is the outline of my talk. I won't spend any time here because I have 59 slides to get through in about 45 minutes. But what I do want to do is introduce our center first. We have a focus on the fundamental and applied research and development of fuel cell systems science. Okay, fuel cell systems science and integrated systems development that itself, and then application to a couple of key major areas, especially the built environment, okay, so stationary power type of fuel cell systems, and to vehicles. We have emphasized over the years high temperature fuel cells. So mostly we've worked with solid oxide and molten carbonate types of fuel cells. But we look at integrated system development for all fuel cell types. So we have some research that has gone on with proton exchange membrane, phosphoric acid, and the like. Our focus is on stationary fuel cell systems. So you see most of the things that we do here is in the stationary realm, but then we also look at infrastructure requirements for fuel cell vehicles and the like. We have some particular areas of expertise. One of them is in the dynamics and control of fuel cell systems, and that's why it appeared in my title as well. Another is in cycle conceptualization and analyses. I will show you many things that we are doing in that area. And then also fuel cell integration with gas turbines and fuel processing. So if you've heard of hybrid fuel cell gas turbine systems like Mitsubishi Heavy Industries is testing here in Japan as we speak, these kinds of systems we've been doing research on for a very long time. As a matter of fact, the world's first one is this one you see here in this picture, a fuel cell gas turbine system that we worked on with Siemens. And then if you're interested in fuel processing and in TriGeneration of hydrogen, heat, and power, we have the world's first system of that type as well, highlighted here at the Orange County Sanitation District. I'll spend a few minutes talking about that as well. And we also have done quite a bit of work in renewable fuel cell systems, and that's what's highlighted in this picture here, where fuel cells and electrolyzers can be combined with solar and wind power in the future. Of course, if you're going to do all those things, you need quite a team. One cannot do that on his own, and so this is the team at one state. We have students that come and go all the time, so we have a team of about 50 people that is typically working in this area. 3 professors that are full-time on one of those, working in the center, and about 10 professors that work periodically with us on different projects. Most of the people you see here are graduate students, okay, doing research with us. So energy systems are important to society and every aspect of our society. They affect all sectors of the economy, and energy is probably the main thing that affects our quality of life, including providing us all the good things, but also having some of the most important negative impacts on the environment. It also gives us freedom. We have freedom because we have energy availability, freedom of mobility. I can fly here. You can fly to the US quite readily because of our energy availability. And there are many disciplines that are required to understand energy and to actually advance energy technologies. I list some of them here. And one really needs to have dramatic advancements in each of these disciplines to make some of the fuel cell and alternative energy technologies work for us in the future. Now, typically what I do when I want to understand or analyze a system is I cannot account for all of these disciplines. So I must make some simplifying assumptions and rely on all of you guys to tell me what I must do with regard to, I don't know, the electrochemistry, or tell me what I must do with regard to the materials I have to consider. What kinds of things must I consider? And then make those simplifying assumptions that I may, and yet rigorously analyze the important physics that affect system performance. So you will see in our approach some things like that. Oops, went back. And one of the key things that our research center is famous for is spatial and temporal resolution, while you are enabled to do full system analyses, even dynamic system analyses. Many people will use bulk models and do dynamics, or bulk models to do thermodynamics. My perspective is that, especially when you deal with fuel cells or other technologies that have dramatic changes across any particular dimension that you are concerned with. A fuel cell, from the entrance to the exit of the anode compartment, has significant temperature, species concentration variations, current density variations that must, I think, be captured to accurately simulate these kinds of systems. So hopefully you'll see that as kind of a theme as I go through a couple of examples. For example, a simplified solid oxide fuel cell model that we have incorporated into the detailed thermodynamic analyses of an integrated gasification fuel cell system. Maybe you have heard of I²CNER before, which is our name for this type of cycle, integrated gasification fuel cell cycle. But I have heard from several people here that in Japan, you call this triple combined cycle. Triple combined cycle. So this is a triple combined cycle. It is quite complex, and yet it has main features of preparing coal, gasifying coal, sending that through some syngas cleanup, because typically the device we use downstream of that, the solid oxide fuel cell, cannot accept dirty syngas, especially the contaminants like sulfur. Okay? That SOFC is typically fed by a gas turbine, single, double, and then a steam turbine, triple, combined cycle. Okay? These types of power plants we have investigated for many years and published several papers on these types of cycles. This particular one that I'm showing here, which I'll show again so that you can look at some more details, also allows us to do CO2 separation, okay, and recycle. There's a very interesting feature of solid oxide fuel cells that enables us to immediately and with very low system efficiency penalty separate CO2 for sequestration. And that is the obvious and simple fact that the anode and cathode compartments are isolated so that you can get a potential difference to generate your current. Okay? Once you do that, you end up in the anode side only having CO2 and water at the exit. Of course, you need a little bit of oxidation because you can't do 100% utilization, but essentially, you can have pure CO2 and water coming out with no system penalty, zero. I still have to condense the water out, but just condensing water out is a lot easier for CO2 separation than other separation techniques. So because of that feature and others, we have shown that you can do this type of triple combined cycle using a catalytic hydrogasifier in this I²CNER configuration that takes advantage of high methane content syngas to produce a 60% efficient I²FC. 60% efficient I²FC with CO2 separation ready for sequestration. Very rarely will you find any technology that comes close to this. If you're going to gasify coal and you're going to convert it in any other way and sequester, nothing can beat this that I know of. So most people would analyze the problem looking at this cycle with bulk SOFC models. And you can see that we, on the other hand, want to actually capture many things that are important for realistic fuel cell operation. So things like the peak temperatures that may occur not at the beginning or the end of the temperature gradients associated with the fuel cell, the species concentration distributions, or even to determine fuel and oxidant utilization, which cannot really be done without a spatially resolved model. So what we wanted to do was develop a simple model that we could include in the full thermodynamic analysis of that plant. And to do that, we resolved only one anode flow channel and one cathode flow channel. Very simple, one-dimensional model of a solid oxide fuel cell. In that model of a solid oxide fuel cell, we resolved the physics of hydrogen oxidation, electrochemical oxidations, methane reformation, and water gas shift chemistry in each of the nodes on the anode compartment, right? And the electrochemical reactions occurring in the cathode compartment as well. And then we need to have good energy conservation to resolve the temperature distribution throughout. And we use the tridiagonal matrix algorithm to actually solve that for all of the temperatures in our one-dimensional solid oxide fuel cell model so that we can do it with computational efficiency. Sufficient to actually take from this system which prepares coal, sends it through a gasifier, puts it through heat recovery and some syngas, okay, cleanup, into a high-pressure solid oxide fuel cell with gas turbine. Compressor feeds directly into that, so this is a high pressure on both sides, anode and cathode. This is a high-pressure hydrogasifier, so you have high-pressure fuel already. You get high-pressure air from this compressor, And then the exhaust of the fuel cell goes through a combustor, which has to be an oxycombustor, because otherwise you don't have pure CO2, right, and water. Then you'd have some nitrogen mixed in. And then that stream and goes through the gas turbine for the fuel, or for the air side, and to separation and sequestration from the fuel side. Does that make some sense? Okay. But instead of having only a bulk model here, which is kind of fuzzy and not well understood, and a whole bunch of assumptions associated with it, I want to replace it with something that's more clear and gives me a good understanding of what's going on in here and whether or not it's even feasible to do this. And that is the one-dimensional model that I just talked to you about. I stuff that back in here and I do the system analyses. And the fact of the matter is, once I stuff it back into this system analysis, I find out that because of this internal reforming SOFC technology, I end up having a peak temperature that's not at one or the other end of the fuel cell, but rather interior to the fuel cell. Okay? Secondly, I must then, decrease the temperature difference that I can achieve for both streams, and to keep the temperature profile within specifications, I must increase the total airflow to my solid oxide fuel cell. As a matter of fact, I must increase it by 4 times to get a temperature difference that's 200 degrees C, already very big for a solid oxide fuel cell. You might say, what's the big deal? I have to increase airflow rate. Well, I'll show you what the big deal is. Of course, if you have a 0D model, you don't resolve any of the temperature distributions, species concentration distributions, and you implicitly assume that the thermodynamics are all that governs this performance. And you get the same answer if you do a 1D model. The thermodynamics would balance and give you the same total energy in, energy out. But in this particular case, if you want to constrain this fuel cell from having a maximum delta T of 200 degrees C, I have to input my fuel, at 650 and only get it out 40 degrees hotter. And I have to input my air at 650 and get it out only 70 degrees hotter. Not nearly the same as a 200 degree overall delta T that I assumed with my thermodynamic model. So how does that affect performance? Here you can see the 0D model and its performance in the same I²CNER plant gives me a 61% overall efficiency on a higher heating value basis. If I input my 1D single-stage counterflow solid oxide fuel cell model, I actually get a little more work out of my cathode exhaust expander. Why do I get that? Because I had to put more air through the system. More mass flow going through that. I also then get a total gross power that I generate that's higher. But look what happens to my solid oxide fuel cell air compressor / blower. It increases dramatically in its power consumption, and the overall internal power consumption very dramatically increases, leading to an overall net electric power that drops substantially, and my overall efficiency goes down to 45%. The end of the I²CNER concept. Oh. Not really, but one must be careful about simulating these systems and account for these kinds of things, like the actual physics and chemistry, electrochemistry, along the length of this fuel cell in order to actually accurately simulate this kind of system. Or else you may think you can get 61% when you can't. So, it's not the end of the I²CNER concept, though, because you can think of pretty novel ways to actually design your fuel cell module that actually could possibly make this system work pretty well. Not exactly the same as the 0D case, because you have to account for this temperature rise, that it occurs internal to the cell. So one idea we came up with was to actually stage the introduction of air, and to flow the fuel through each of the same stacks I'm not designing the stack any differently. Every stack is the same, so it's not like a complex stack design. Every stack is the same. But now what I do is I put air in at 650. It comes out at 713. I add some air at 330, which is just the compressor exit temperature. And I do this in a 4-stage solid oxide fuel cell module that ends up having the air coming out then at 753 C. Okay? And I achieve an overall fuel utilization, that's 73%, and an overall air utilization of 45%. Also maintaining for every single one of these fuel cell stacks about the same temperature distribution. And then my system becomes quite a bit better performing than that case where I only had one flow of air, one flow of fuel, leading eventually to this achievable efficiency of 58% or so. So the I²CNER concept that gives us this potential to sequester CO2, to achieve really high efficiencies, and even produce hydrogen as a byproduct is feasible, but it should be analyzed with a spatially resolved model. So similarly, when you analyze the dynamics of a fuel cell system, I think that you must account for spatial and temporal resolution of certain features of the fuel cell. Our approach has typically been in MATLAB Simulink, where we've developed a modeling framework for solid oxide, molten carbonate, proton exchange membrane, all the fuel cell types. And we assume quasi-steady electrochemistry because usually the electrochemistry is quite fast when it comes to comparing it to the dynamics of the thermal performance of the system and the fluid flow performance of the system. But we also always include some form of geometric resolution. This is an example of some of the equations that we would solve typically in each of the nodes of a dynamic model of a solid oxide fuel cell. So we'd include things like the species conservation, the momentum conservation. We would calculate the local Nernst potential and the local loss terms associated with the electrochemistry. And then we have the dynamic mass conservation equations that we would have to solve for each of the nodes. And we would resolve it in simple geometries like this, right? Like a 10-node planar solid oxide fuel cell that would have an anode and cathode compartment and interconnect plates. Or in a tubular fashion with cylindrical coordinates solving similar sets of equations where you can even have complex heat exchange with regard to an airflow pipe, for example. This was like the Siemens type of design. And then the preheated air flowing against the cathode, and then the fuel flowing around the outside. So similar, but spatially resolved in cylindrical coordinates, tubular solid oxide fuel cell. An important thing to resolve is the heat transfer. And in many systems, even radiation heat transfer must be resolved. And so you see radiation terms, convection terms, and conduction terms, all of which must be solved to accurately predict the temperature distributions. And then we have verified these modeling tools by comparison to dynamic measurements of systems that we've made in all kinds of different systems. I'm only showing a couple examples here, but this is for like a carbonate single cell test stand where we've used our dynamic models to predict this. This is for a solid oxide fuel cell system, a standalone system. This is for a solid oxide fuel cell gas turbine system where we're predicting some of the dynamics of that performance. And then we can use these modeling tools with spatially resolved physics in the fuel cell to actually design some systems that can be controlled and determine what kinds of controls must be applied in order to keep the solid oxide fuel cell in safe operating conditions. So for example, in this case, I'm looking at a solid oxide fuel cell gas turbine system. It has, of course, the compressor where the air comes in. It's preheated. It mixes with some of the recirculated cathode off gas, goes into the cathode. And then we have an oxidizer downstream, mixes some of the anode and cathode gases. That goes to the preheater, exchanging some heat here, and then to the turbine, and to the fuel preheater, fuel going into the SOFC on this side. So what we can do in this particular case is manipulate certain variables to control this system under dynamic operating conditions. So I'm manipulating this recirculation blower power, the fuel flow rate going through this, okay? The air preheat bypass valve. So you can see here, this is a bypass valve. I can either preheat the air or I can bypass that and send it directly to the mixer. And the solid oxide fuel cell bypass valve. So that's this valve that you see here. Okay, so I can either send this recirculated here or send it directly to the turbine. And then what I'm going to do is I'm going to subject this fuel cell, a solid oxide fuel cell that almost everyone will say has to be base loaded. Do you agree? Solid oxide fuel cell has to be base loaded, right? No. I say you can dynamically operate a solid oxide fuel cell. And I'm going to subject it to a sudden decrease in power. Okay, a sudden decrease in power from 100% full power to 50% full power. And if I control these parameters that I showed you earlier sufficiently, I can maintain my temperature distribution in a reasonable fashion so that I don't cause a lot of thermal stresses. This is my temperature distribution for a cross-flow cell that I resolved in 2 dimensions, only 25 nodes. You can see it's a very simple model of the fuel cell, but I can resolve the airflow direction and the fuel flow direction and get this temperature distribution during the dynamics that I subjected this to. And we have shown that you can actually operate these kinds of systems and very well keep the temperature uniform. In this particular case, I kept the peak temperature below 1073 and the peak gradient between below 150 K. So how about a standalone solid oxide fuel cell? In this particular case, I'm dealing with a solid oxide fuel cell system that has only heat exchangers, some steam preparation and a reformer, and an air blower. It's not as complicated as the previous system, but I still need to manipulate 3 variables, my fuel flow, my blower power, and my bypass valve. So this is the blower power, here's my fuel flow, okay? And then this is my bypass valve. So this determines how much air preheat I have going into this solid oxide fuel cell. And what I'm trying to do is control the system power, meaning some kind of dynamic perturbation, and the peak SOFC temperature and the temperature profile. Okay, in this case, I'm going to ramp it up from 25 to 75 amps of current and see what happens to the pen temperature. So this is on a logarithmic time scale, mainly so that I can see this transient that occurs here when I manipulate the current, okay? This is what happens to the reformer temperature. It drops, okay, because I end up performing more endothermic steam reforming reactions in that reformer. And then these are the control actions that my particular controller in this case took, where I ended up taking the bypass valve down to fully closed for a while. Then I opened it up a little bit and ended up settling at a very much lower overall bypass. And you can see here the blower power that was changed in this particular way and the blower speed that changed in this particular way. And what happened to my temperature distribution and my current, this is just shown at 2 or at 4 different times after that perturbation. At 0 seconds, I perturb it. This is what my current distribution looked like, and this is what my pen temperature distribution looked like. But then at 874 seconds after that perturbation, of course, my current is a lot higher, and it stays about the same. Okay? And my temperature slowly changes, so that afterwards I have still a very reasonable temperature distribution, and not one that varies substantially from that which I started out with. So, we can also apply this to many other types of systems, and I put these slides in here recently because I wanted to talk to you guys about a few topics that are close to my heart. One of them is this particular idea of taking a high temperature fuel cell and producing not just power and heat, but power, heat, and fuel. We call this TriGeneration. And the idea is you take some of what would have been thermal output and you use that thermal output to overcome the endothermicity of fuel processing reactions. Very simple idea, but it has profound backwards benefits and synergies with the system that can be exploited. Okay? And after working on this topic for about 10 years, we finally worked with Air Products and Fuel Cell Energy to actually build one of these things at the Orange County Sanitation District that uses waste gas from a wastewater treatment plant. A wastewater treatment plant that actually produces digester gas that typically would be sent into a boiler. We've replaced that boiler with a fuel cell. We needed to introduce some fuel treatment because some of the contaminants in anaerobic digester gas cannot go directly into a fuel cell. But then we can take that fuel cell and use the waste heat to provide heat to the digesters, which is needed. And it well integrates at the temperature that the exhaust of the fuel cell starts at. And we can produce AC power. But in this particular case, we are also producing hydrogen from this high temperature fuel cell and separating it, compressing it, and dispensing it to hydrogen fuel cell vehicles. So we are doing this in Orange County, at the Orange County Sanitation District, just about 2 miles north of Irvine. And I don't think you've seen this yet, but next time you come, I'm going to show you this plant. Because it's a very cool plant. We have the actual hydrogen production facility right here, next to some of these settling ponds, and then the dispensing site right next to the freeway, okay? Right up here in Orange County. And we've achieved 54% hydrogen and power production efficiency with this system. This doesn't count the heat, it's just looking at the two products that I mentioned, hydrogen and power. And we've dispensed more than 3,000 vehicle refills with renewable hydrogen. Hydrogen that comes from our sewer system. Pretty cool, right? And this is what the plant looks like. Okay, so it's a pretty complicated plant. A plant that has many different components that you can see here. The first component is this anaerobic digester gas cleanup skid. And it has to remove especially sulfur, but also siloxanes from the gas. And then we have mechanical balance of plant. This is where we do the heat exchange for the air preheat, where we add water to the fuel stream, and where we do some anode tail gas oxidation. Okay, so this is the combustor that sits at the end of the anode. Okay, then we have the fuel cell, which sits right behind it. You can hardly see it behind the plumbing here. And then the inverter, which converts our DC to AC. We also have special equipment for TriGeneration, because now we take the anode off gas and we convert that to pure hydrogen and the rest of the stream. And to do that, we first put it through some water gas shift reactions here. Okay, we put it through a syngas compressor, and we have to boost up the compressor a little bit so that we can actually separate the gas in a pressure swing absorption skid. And then we take the pure hydrogen through high pressure compression to store hydrogen in these cylinders that you see right here. And then we have a pipeline that we've installed that takes the hydrogen all the way around to our dispenser near the freeway. TriGeneration of hydrogen, heat, and power from waste gas. We've also looked at renewable fuel cell systems, and in particular looking at taking solar power and enabling it to be used in a residence dynamically by storing the otherwise curtailed solar power, or solar power that goes back onto the grid, and using it for generating hydrogen during the day, and using the hydrogen for two purposes. The first is, of course, running through the fuel cell at night when you don't have sun available, and the second is to refuel my vehicle, which might be pretty cool. So we took our system here. This is our photovoltaic system that we used. This is an electrolyzer, a fuel cell, hydrogen storage that we used. And we simulated the actual residence. We didn't install this at a residence, but we made actual measurements at the residence so that we could actually see if the dynamics could be met by this kind of a system. Because the dynamics of an individual residence are quite demanding. You can see here that this particular residence usually only takes about a half a kilowatt of power. That's it. But sometimes wants as much as 8 kilowatts. These kinds of dynamics are very challenging to meet with a single system, but if you had smoothed this throughout to, for example, provide this sort of service to the whole neighborhood, it might work out. Okay? But these dynamics could be met if we design our fuel cell system to have 4.2 kilowatts, our electrolyzer to have 7.9 kilowatts, okay, of capacity, okay, and a little bit of battery power. That's the only way we can make this work. And that makes the system not very economic for meeting the highly dynamic demands of a residence. But it did work, and we could dynamically dispatch it just fast enough and produce enough hydrogen in excess for an 18-mile weekday commute. So Professor Shao here is doing some similar research, looking at these kinds of concepts where hydrogen energy storage might be used with renewable power. Okay? And renewable power has its challenges and needs, I think, for hydrogen and fuel cell technologies. Both, I think, will be essential for our sustainable energy future. There are some challenges associated with renewable power dynamics that I will discuss in the next couple slides. We worked with Pacific Gas and Electric to actually simulate real circuits in their territory. This is an example of one. It's called the Cayetano circuit, and you can see the geographic layout of this circuit. And you can see that it has a lot of individual transformers. Those are all the green dots. Some individual solar systems. You can see these magenta diamonds. Those are the PV systems that are installed. And it's a fairly high PV penetration circuit already. It has 15.6% of the peak power is produced by these PV systems. So what are some of the challenges associated with this? Well, the traditional way of managing the flow of power and the voltage distribution on the circuit must be changed, and sometimes equipment must be added to keep voltage within limits. So you can see here, for example, we looked at that circuit in its original configuration, and then we also added various amounts of PV power to this system, and you can see the voltage distributions change quite substantially, and sometimes with very high voltage levels near the end of the circuit, because we have substantial backflow of power toward the substation. Sometimes they can get well out of bounds, and the traditional control strategy using a load drop compensation method, I won't go into details there, but can exacerbate the problem, hinder the achievement of voltage within limits. Okay, so one must do something different if we're going to use a very high amount of power on individual circuits. Very high amount of solar power on individual circuits. And then we can look at the whole system. This is a simulation of Southern California power while we actually meet the 33% renewable power requirement of our law. Our law requires 33% renewable power by 2020. Okay, by 2020 we must have 33% of our power met by renewables. In this particular case, we're meeting it mostly with wind power. And what you can see here is the actual California demand. Okay, Southern California demand. That's what this blue line is here. And you can also see the wind power that we get from a wind turbine model and a wind, not a wind turbine model, but actually a whole wind farm model, okay, and real measured wind data. Okay, and this is a 10 gigawatts of wind power installed. So here you can see it's at about its full capacity, and other times it's just going up and down during that same week that we made this measurement. So do you see any challenges with this for the grid? You may see a couple of them. How about this one right here? What's wrong with that? This is how much power all of the other generators on the circuit must provide at this one instant in time, right here, okay? So it means what with regard to the generators we already have installed on this circuit? What does it mean? I have 33% of my power now coming from renewables, but I need every single one of the power plants that I already had to be available in case I need them. Every single one, even at 33%. That's a challenge. How about this one? Is this a challenge? Now I have power plants that wanted to be on, that are base load power plants that have to shut off if I am to accept the wind power. They're not going to do it. Nor do I think they necessarily should do it. They should keep those base load plants running. How about this? In the middle of the day, all of a sudden, because this wind power suddenly shoots up, I have to shut down a very large fraction of the plants that are used to operating in the middle of the day. Or turn them off and then turn them back on an hour-by-hour basis. No way our plant's going to be dispatched in this way. And having unprecedented ramp rates required that perhaps the independent system operator can't even manage. So these are some overall grid challenges associated with introducing a very high fraction of renewable power. And this temporal resolution of the balanced power dynamics is very important to understand. Because if we balance the power with traditional load-following power plants and peaker plants, which is what we use today, use the same here in Japan, what would happen to things like our CO2 emissions or even our air quality? And we did some simulations of that. So for example, these are the power plants that are inside the Los Angeles Basin that were dispatched according to the dynamics that I showed you in the previous diagram. And what happens to our particulate matter is we see increases of 1 to 2 micrograms per meter cubed, especially in the eastern portions of the basin, that occurs as a result of dynamically dispatching those power plants. In addition, ozone concentrations increase in our basin because we are introducing more wind. I introduce more wind and I get worse air quality because of dynamics. Interesting. So one of the things that we could do is to scale up that type of hydrogen storage system that I talked about earlier, that was not economical at the residential scale, but use it instead for massive energy storage at the grid scale. Okay, and in this particular paper, we did a little study looking at real power dynamics, okay, that's what this magenta line is, and real wind power, that's what this green line is, okay, for a typical week in Texas, in this particular case, okay, in Texas, where we have a lot of wind power and wind farms, okay, and then what we used is, we used a salt cavern to actually store either hydrogen or air in a compressed hydrogen or compressed air storage scenario. When it comes to needing massive amounts of energy storage, some of these kinds of systems, I think, are quite viable for storing massive amounts of power and energy. And so we're looking now at, can we actually dispatch these things dynamically to do this? And what we're showing here is these are the, for example, the net power, okay, that is being stored now, okay? So this is when I'm actually storing some, and this is when I can actually need to dispatch some from my energy storage in this particular week of the dynamic. And what I'm doing in this particular case is I'm comparing compressed air energy storage to compressed hydrogen energy storage. And this is the same cavern that is being used for the air as is being used for the hydrogen for a 1 week of operation under these conditions. And what you see here is that the air storage is often not able to store any more power under conditions when there's a lot of excess wind because it has no more capacity within the pressure limits that are allowed. whereas the hydrogen storage can fit a lot more energy as hydrogen into that same cavern and never reaches its maximum pressure during this 1 week of operation. And sometimes the minimum pressure is realized, whereas the hydrogen is able to continuously dispatch during that 1 week. And if you simulate this for an entire year, using measured wind data, measured power demand, and this dynamic dispatch of hydrogen, we can see that the compressed air energy storage cavern is often completely maxed out or completely empty, whereas for the case of the fuel cell and electrolyzer hydrogen storage, we see that we can actually even shift storage. We can store wind power in the springtime and actually dispatch it in the summertime. We can shift power not only from day to day, but also from season to season, using a higher energy density storage mechanism like hydrogen energy storage. Okay, about how much time do I have left? What does it look like? 5 minutes? 8 minutes, okay, and then I'll have some time for questions. Thank you very much. So I'm going to talk a little bit about network and grid impacts. I think one of the areas that I saw some of you starting to talk about when I visited you is smart grid area. It is a very hot topic right now. I know maybe not, maybe only just a hot topic in name, but there are many smart technologies that I think must be implemented in order for our types of ideas to really gain hold and be used in the market in the end. And we are fortunate to work with the U.S. Department of Energy and Southern California Edison on what is called the Irvine Smart Grid Demonstration Project. And this is a satellite view of the Irvine area, and this is our campus, UCI, right here. And the Irvine Smart Grid Demonstration Project starts at the MacArthur substation here, okay, and we have two smart circuits. One is the Arnold circuit, you saw it go there, and the other is the Rommel circuit, okay? Couple of key things here. You can see the circuits have some loops in them, and you can see the circuits touch each other in a couple of places. This is not typical circuit design, but design intended to look at loop circuits and enhanced reliability by letting circuits share some of the power demands and meeting some of those power demands. Okay? So those are a couple of things that this introduces. But we have a lot of smart technologies that we are introducing, and one of them has to do with how do we smartly charge electric vehicles. Because if electric vehicles are going to be used substantially in the future, they first of all need to be managed well so that the grid can support it. But secondly, if we're going to use vehicle-to-grid technology for managing some of this dynamics of renewable power, we need smart technology to dispatch it. And I'm not going to go through all the details here, but what you can see is we have 4 separate streets in an Irvine neighborhood that introduce various levels of smart technology. One of them is a control group, only being monitored. Another one introduces community energy storage at the transformer. The other one, energy storage at each of the homes. And another street is a zero net energy street. Okay, and these are all interconnected back through to this MacArthur substation, and we're introducing electric vehicles at these places, and these universal remote controlled interrupters. These are what allows us to share the power amongst the circuits. Okay, that's all I think I'm going to say on this. Okay, our campus, another picture of it, this time showing us close to the beach. So I encourage all of you to consider coming and visiting us. Very nice place to live and to do research. So I want to have some interactions with you guys. It'd be nice to have you come here. This is our campus again, the Central Park right here. And I want to show you a couple of additional features of our Central Park in our plant. This is an industrial park on the edge of our campus. And then we also have that, I told you about the 4 streets of the I²CNER project. They're located in this University Hills housing area that you see here. This is where our center is. You remember this picture maybe from the front page of my presentation. It's sitting right here on this edge of the campus. And this I²CNER project is directly adjacent to our campus and our campus microgrid. Okay? So our campus microgrid is centered around this central park. It has 10 independent 12 kV circuits, each one owned and operated fully by the university, and a single point of interconnection with our local utility, Southern California Edison, coming from the same MacArthur substation as our I²CNER project. And we have a twin combined cycle, not triple combined, but just double combined cycle plant. Using natural gas combined cycle, we have both gas turbine and steam turbine, can produce up to about 21 megawatts of power that we dispatch at our central plant. We have thermal energy storage so that we can actually produce chilled water at night and then use that chilled water during the day to provide all the air conditioning for the main buildings of campus in a district heating and cooling circuit that goes around the campus. We also have rooftop solar. We have about a megawatt total. And we're going to introduce 2 or 3 additional megawatts like you see on the top of this building here. We have some concentrated solar photovoltaic on 2-axis tracking systems at UCI. We have zero emission vehicles that are battery electric vehicles that we are using at UCI, and we want to control those also to dispatch them in complementary ways. And we also have a 180 kilogram per day refueling station for fuel cell vehicles, which have been driving these types of fuel cell vehicles for the last 8 years, especially with Toyota. And then we have a 300 kilowatt fuel cell absorption chiller system that we are going to install this year, and that's going to actually provide cooling, heating, and power for our system. And then the system circuitry looks like this geographically, which you can see the central plant located over here, the single point of interconnection. And then what happens to our, the whole idea is to try to save money for the campus by dispatching these things properly, controlling them properly. And this is what happens during a typical day, is you will see that the real campus demand is indicated by this blue line that you see here. And we dispatch the combustion turbine generator so that it produces almost its maximum amount of power for the gas turbine, not the steam turbine, it's just the gas turbine portion, for a large part of the day, and it goes down a little bit in this time period here. The steam turbine is dispatched, as you see here, but it has to be shut off in the early morning because we have other heat demands in the early morning that require the steam and take preference over generating electricity. And then you see the solar power coming up in the middle of the day so that our net demand from the utility looks like this. And what we're trying to do is to minimize the amount of power that we consume, but also minimize demand charges, okay? And this way we can actually lower the cost of the operations to the university. Okay, one final thing. You may or may not know that we in California are dealing with a problem that is very similar to that of Japan. And that is the fact that we have shut down in Southern California our 2 gigawatt nuclear power plant. This is the San Onofre nuclear generating station. Okay, here's a picture of it. It was originally shut down in January of 2012 due to some heat exchanger tube problems. Okay, there were some corrosion problems on these tubes. They were replaced and the whole plant was ready to be started up again until the public objected. And they objected for a couple of reasons, but mainly because they saw what happened in Japan. And in June of this year, SCE finally relented and said, we will never start it again. This leaves a very big hole in our power generation demand in a very high demand portion of our Southern California area. Very, very high population, very high electrical demand, and we need to figure out some kind of solution for meeting these power demands in this area right here. And the key thing that we're starting to look at right now is where can we put fuel cell systems in this grid network, and how should we dispatch them to support what used to be a large nuclear power plant in this region. Okay, maybe a little bit longer than 8 minutes, but I presented a whole bunch of integrated system analysis analysis techniques and our application of such that I think show that fuel cells have essential characteristics for achieving sustainability in the future. They're clean, they're efficient, they're dispatchable, and fuel flexible. I think we also can agree that spatial and temporal resolution of the important physics is essential to making these systems work. I provided some examples of application. Okay, a simple spatial SOFC model, some dynamic fuel cell models and controls that have to be developed, energy systems for high renewable penetration and utility grid network impacts. But there are so many things that we still need to advance, and we need advancements in many, many disciplines. And I am very excited if I will have the chance to work with so many of you who are making very important contributions in many of these areas. These are some funding agencies and collaborating faculty and colleagues that have helped me with this. Thank you for your attention.